This video is going to cover how to do a sample ECM calculation for a replacement boiler. So this is for the Stanton campus of Delaware Tech, and I want to cover with what's in the building right now. So this is a picture of the building automation system, and what used to be in the building was a Kiwani boiler, and right now that's completely off, and it's not even hooked in to run the system because the campus purchased 3 condensing boilers. Those are what these pictures are here. And that's what really supplies the hot water to the building now. So this was a relatively warm day. It was 50 degrees outside, so it wasn't supplying very high temperatures. But that's what you can see. So what we're going to do is set up a situation where the campus wants to know now, by replacing this boiler with these 3, how much money did they save? So first off, let's just look at some of the spec sheets from these boilers. So down here we have the Airco Boilers, which are the 3 condensing boilers here. And you can see the model is BMK 3.0. So that actually means the 3.0 means 3 MMBTUs, or 3 million BTUs. And it doesn't actually give us too much more here. It gives us some of this, combustion calibration and stuff, but it doesn't really give us much more stuff. We can get more from the manual, and I'll show you some of the things that I got from the manual, but that's the basic idea. It's the BMK 3.0. Okay, and then we look at the blueprints, and it doesn't have the Kiwani boiler. It has a Cleaver Brooks boiler, but I'm pretty sure that this, the Kiwani boiler either replaced this, or maybe they had written this in, and these were not the build mechanicals, but the ones that they spec'd out. So it's really hard to see, but I'm pretty sure it says 6695 output and 8300 input. So so the output is about a little bit more than 2 of the condensing boilers, which makes sense because that just means the third one's for redundancy, as well as it's better to run them part load anyway. Okay, so now let's go into more of the curves. So these curves are pretty much a mess, but they give you an idea as to how these boilers operate at part load. And this is actually really important because if you think about it, a boiler is only operating at its sort of design condition at full load for only a couple hours every year. So it's really important to see the efficiency at part load. So first off, let me just show you where I got these part load curves from and show you how I calculate them. So first off, the performance curves come from sort of a California standard, and you can see the website here if you click here. But it's really nice. These curves actually give Energy Plus curves and DO2 curves, and some that are compatible with both Energy Plus and DO2. So if we go down here and we scroll down to the boilers, they have a hot water boiler. Let's just scroll over a little bit. They have a hot water boiler non-condensing. I think they mean condensing. And they have a hot water boiler condensing. And they have the equations for both of these things. So if you see, they have it's red is the one we want to use because we want to use the Energy Plus versions, because I have the documentation for Energy Plus up. But these are quadratic and biquadratic, and here are the coefficients. So yeah, this is totally unusable in this form if you have never done this before. So I also have here sort of what that means. So this is from Big Ladder Software. They keep all the Energy Plus documentations online. And here's what the equation means. So you have your A0, A1, A2 for quadratic. Those are just coefficients. And then PLR is your part load ratio, and that gives you your efficiency. And then for the biquadratic, you have the same coefficients, you have more of them, and you have the part load ratio, but you also have the entering water temperature, and we'll see that that's important for the condensing boiler. Okay, so that's why I have these things up here. So this is, for non-condensing, it's quadratic, so you would use this equation, and for condensing, it's biquadratic, and you can see there's a lot more variables all the way up to A5, and so you would use this equation. So what does that mean? Well, let me show you before I show you how to use these coefficients. Let me just show you what our boiler, the BMK 3000, looks like. So we have the return water temperature, which is actually the same thing as the entering water temperature of the boiler, and the efficiency. And you can see that it generally goes up at lower return water temperatures, and it's the highest efficiency at low return water temperatures and at low input, so low firing rate. So that's where the highest efficiency occurs. So now, but if this is hard to model, we need an easier curve. So that's where these coefficients in the biquadratic comes into play. So I'm not going to go over all the calculation details, excuse me, but basically if we assume a part load ratio, an entering water temperature, and we have to convert that to Celsius, and then a boiler efficiency fraction comes from using the equation, the quadratic equation over here, and the A0, A1, A2 that came from the ECM, right? We can get our non-condensing boiler efficiency. We do the same thing with the condensing boiler efficiency. And that gives us what's going on. So that's the idea here, is that you can use these equations to help you out. Now, we want to be careful because this is a normalized boiler efficiency. So what you need to do is you need to take that to get the actual efficiency. You need to take that and multiply by the nameplate efficiency. So that's what I do in these columns. Okay, and so these are the curves that we end up with. So this is the condensing boiler, and you can see that it's not perfect, but it's similar to this. It goes up at high or at low entering water temperatures, and then goes steadily down. So, and this would be like the cyan curve here. So this is for the 60% input. So not perfect. And then I don't have another curve for the Kiwani. It's too old. But this was what the non-condensing boiler. So when you have a non-condensing boiler, actually at part load ratios, the efficiency goes down. So the efficiency can be as low as 50% at really low loads, and then goes up to it's about 80%. All right, great. So now we got those curves, but how would we use those curves? Now, I want to just point this out. These are these are sample calculations. You do not want to use this list. What you're going to do is you're going to do the same calculation for every single hour of the year using these coefficients. So this is just for your reference. So don't use any of these numbers below. You're just going to be actually using all this stuff in the next page. So let me show you what this looks like. And since I'm having you do a lot of this, I'm not going to go through all of this, but I'll sort of just talk about what each of these columns is. So all this red comes directly from the EMS system. And this is all the data they had on the boilers. They didn't have any other data. So they have firing rate, which is great because that's basically part load ratio. Be really careful because you want this to be either a decimal or a percentage. So this would be 0.19, so divide by 100. So whenever you do your equations, make sure that you divide, when you're looking for part load ratio, you divide by 100 here. And also make sure that you use Celsius for any temperatures that you have. So that's more like the supply temperature. The other assumption we're going to make is that return temperature and supply temperature is just a 20-degree Fahrenheit difference. So so basically you're going to take the supply temperature, the entering water temperature is going to be this minus 20. So in this case, it would be 117 degrees. And then you have to convert that to Celsius. So you can see we have supply temperature and firing rate. And then we can get return temperature by subtracting by 20, which is exactly what we need if we look at these curves. We need the return water temperature, and we need the part load ratio. Or the other way to think about it is over here, for the biquadratic, we're going to need the part load ratio, which is the same as the firing rate, right? And remember, that's in decimal, so make sure you divide by 100. And we need the entering, if you see TW is boiler water temperature, and it needs to be entering. So that's what the T sub W is. All right, great. So now we go over here. This is just the entering water temperature. So again, in this case, we take for the boiler 1 supply temperature, subtract 20 degrees and convert to Celsius. Then to calculate the efficiency, because this is the condensing boiler, we're going to use this formula and these values, because this is for condensing, for A1 through A5. That's what this is. Same thing for boiler 2 and boiler 3. It's the same exact equation, just using the different information from the EMS for each boiler. This is just to show you the total firing rate for all the boilers. So this can be above 100% because if all the boilers were outputting maximum, this would be 300%. So then what we do is we convert that to output. So we have the efficiency and we have the firing rate for each boiler. We can convert that to output. Then using the output and the efficiency, we can find the input of each boiler. Then we know that the Q1E output is the addition of all of the outputs of the condensing boilers. Because remember, output is always the same when we're comparing different HVAC systems. Because you want to output the same amount of heat to the building. So you can see that this is just the sum of these three numbers. Then we calculate the part load ratio using the assumption up here of our Q1E boiler has an output of 6.695 MMBTUs. And then using the part load ratio and this formula, it's quadratic, then we can calculate the efficiency, and then we have the output, we have the efficiency, so we can get the input. And then it's as simple as doing this for every single hour of the year. So this is the TMY3 data for Wilmington, Delaware. Or actually, no, this is actually real data from the building management system. So we do this for every hour of the year, and then we sum it up to get our total MMBTU usage. So that's it. So thank you for watching.